The IO type in Haskell gives us access to all sorts of side effects. We can access the disk or the network, we can have mutable state, we can do concurrency and many things more. But there is a price, a well-known price, I guess. There is no safe way to escape IO. Once you have a computation that is somehow dependent on side effects, there is no safe way of pretending that it isn't. There is perhaps slightly less well-known a subset of IO available in the type ST, where you have access only to mutable variables and nothing else. And in ST, you can actually escape. There is a function runST, which is supposed to be safe, which allows you to wrap up a stateful computation where you can locally allocate some mutable variables, modify them as you like, and in the end, you from the outside pretend that this was just an unobservable temporary access of mutability that you can no longer observe from the outside. But the type of runST is slightly strange if you've never seen it before. It has a so-called rank 2 type, and that may be surprising at first. Why is it necessary? But it turns out that it is actually necessary to have this type in order for the operation to be safe. And in this episode of the Haskell Unfolder, we're going to hopefully demonstrate why.
Yeah, so welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, the show is live streamed. We invite you to submit questions or comments in the chat, and we will try to show them on screen and discuss them.
Yes, okay. So to start, let's look at a simple example that involves this ST type. And it's a somewhat contrived example. This episode isn't really about motivating the need for ST. There are more interesting algorithms. Often they involve some array computations where you really want to modify the array in place temporarily. But here, what I'm trying to do is have this function classify, which takes a list of integers, and I simply want to count the numbers in the list, or the number of integers in the list that are strictly negative and strictly positive, and return them as a pair. And the way I do this is by allocating two strefs of type int, which are both initially 0. That's these two new stref operations. Then I'm locally defining a function step, which is describing what we're going to do with every single element of the input list. And namely, we're going to compare this with 0. If it's negative, we're going to increment the neg counter. If it's greater than 0, we're incrementing the pos counter. And if it's equal to 0, we're not going to do anything. And then we're using mapm underscore to call the step function on every element of the list, and we're not really interested in the results here, only in the effects, namely the increment of the counters. And then after we've done all this, we're going to read the final value of the neg and the pos counter and return as a pair. So we can hopefully try this out by saying something like classify on an input list, which has here 1, 3, and 4 as positive numbers, and -2 and -5 as negative numbers. So there should be 2 negative numbers, 3 positive numbers. So I'm expecting the result 2, 3. So let's try to run this, and indeed we get that result. So that's good. Okay.
Just to be clear, this example, you could write in normal Haskell. You don't really get any benefits from ST here. It's just an example.
Yeah. I mean, in most cases, to be fair, you could write things in ST also in other ways, but sometimes you get a performance benefit, I guess.
Sure, but here, exactly.
Yeah.
The performance
but here you not even get a
reusable.
performance benefit.
Exactly.
Yeah, that's true. Okay. So let's look a little bit more at the interface that we're actually using here. So we're using new stref, and new stref takes an initial value, and then in the st monad returns something of type stref of a. And you can see that there is this additional argument s, which is part of what we're going to talk about today, which is not really that easily explained, right? So there is this, but if you just ignore that for the time being, we are producing something in the st type, and it is of type stref, and the a is the type of the variable, right? Which in our case is int.
Yes,
and then
stref is a mutable variable, right? That's what this is.
Yeah.
A reference is another name for a mutable variable.
Yeah. And then readSTref is taking such an already allocated reference, and it's producing the current value, which is again because it can be changing, is in the ST monad. And then we're not directly using writeSTref here, but I'm listing it anyway. And so there is a strict and a non-strict variant of writeSTref. We're only using the strict one here, which has the prime. But the type is the same for both. So writeSTref takes an stref and takes a value, and then overwrites the current value, assigns essentially the new value to the reference. And modifySTref can be implemented in terms of read and writeSTref. It takes an stref and it takes a function and basically applies the function to the current value. And again, we're not really interested in the result, we're interested in the effect. And then there is one more function which I have omitted so far, which is runST. So let's look at the type of runST as well. Let me actually just ask GHC for the type of runST. And this one has a slightly surprising type because so it's going from STSA to A, but there is this inner for all here. Like usually, whenever you see a type signature in Haskell, we usually don't write that, but all type variables are universally quantified, right? So basically for all 4 of these, you can imagine that they are something like this, in fact, right? For all SA. And what that means is the user of the function can choose at which types S and A to invoke this, right? There is flexibility in the use. But here, we have an argument which is universally quantified, and that is usually saying something that the user is limited in the choice somehow, and therefore the implementer gets more flexibility. But it's not immediately obvious why this is useful here or why this is needed, because if you look at it, S does never really seem to be instantiated to anything. It does not really seem to have much use. It's not completely clear why we need to do it in such a weird way. And this is what we're going to look at now. And typically, if I don't fully understand something and I cannot immediately find a paper or a blog post that explains it to me, I often take this sort of slightly adversarial position and say, why, I'm just going to do my own thing. I'm going to do it better. Or well, in this case, I'm not really believing that I can do it better, but let's just try. Yeah, or worse, right? Let's just try to do it differently. Let's just try to do it simpler, and let's see if it breaks somehow, right? And so that's what I'm going to do now. And I'm actually going to completely replace the implementation of ST. We're going to go back to the original one, but for the time being, let's write our own simulated version of ST and let's simplify it. And I want to simplify it in 2 ways. One is I want to get rid of this S parameter completely for the time being, because that's the point. We want to analyze why is it needed and why is this rank 2 type needed. But a second simplification, which is actually orthogonal, that is really just to keep it simple, is that I'm going to pretend that all strefs are of type int. That also makes it a little bit simpler. So our simplified interface is going to look like this. We have no S argument, and we are assuming that all refs are of type int. So we have new stref, which is of type A2, and now it's just st, no S argument, and of stref. Stref does not take any argument anymore.
Should that be int rather than A?
That should be int, yeah. And then readSTref is taking an stref and giving us an st of int. WriteSTref is taking an stref and an int and is producing an st unit. And modifySTref is taking stref and an int-to-int function and giving us an st unit instead as well. Okay, so next let's look at what we are actually going to do in order to implement st and stref. Okay, so I'm going to simulate st as just a stateful function that takes some store, right, to a result of type A, right? We still have st of A as a parameterized type. We have st computations that produce results of some type, and a new store value. And this is sort of the typical pattern of the state monad in Haskell, which I'm going to use here. And eventually I will need this to be a monad because I want to re-implement the classify function that we've already seen in my simulated version, right? And that is using do notation, and for that I need this to be a monad. So therefore I'm going to derive me a couple of instances, but we're not initially going to actually use them. Let's look at the remaining important data types. This store here, well, primarily we want to hold the memory for all our variables, right? And this is why the simplification of assuming that we only have integer variables pays off, because then we can just use a vector of integers. Otherwise, we would need to use some sort of heterogeneous data structure, and I did not want to go there. So here, we're just going to use a vector of integers. That's the current values of all the integer variables we have allocated. And then from time to time, we're going to allocate new integer variables. And sort of the next one we can allocate, I'm going to store here in the store as well, using something of type offset, and offset is just an int. That's supposed to be a reference into the vector, and is always going to be the length of the current vector, so the offset, the index of the next allocated variable. And then an stref is simply an offset, right? Because like every time we allocate a variable, we assign it an index into the vector, we make the vector one element longer, and that's it. So with this preparation, it's relatively straightforward, hopefully, to define all the functions that we need. So let's see. New stref is of type int to stref. And so this is taking this initial value that we have. Let's call that I. And I'm going to just write all of these directly, like just as functions from store to pairs of a, comma store, to show that these are simple functions. So we have make st, and that takes a store input, and that store input is actually something of type make store with the current memory and the current next. And then we have to produce a result, and the result in the case of new stref is a new stref. So that is this make stref, and we're going to use this next offset that we have readily available in our store already. And then we also have to return a modified store. And in the case of new stref, that is actually a substantially modified store. We have to extend our vector with one new element which contains the value I. So I'm going to snock. So that means append in the end a single element to the memory, an I. And this is an inefficient operation, right? But here I'm interested only in semantics and in eventually why the type of runST is necessary as it is. So even though vector snock is a sort of like a linear array copying operation, I don't really care right now. It's
and actually, probably in reality, it probably also doesn't matter too much, probably, because you probably won't be allocating variables in a loop.
Yeah, probably not, but you could possibly have computations.
There might be examples, sure.
Yeah, exactly. And then we have to increment next by one, okay? Because we have allocated one variable, and the next time we allocate, we don't want to reuse this. Okay, so that's new stref, and the other ones are equally simple, or perhaps even simpler. So read stref is taking an stref and it's producing st of int. So here we're getting an stref which contains an offset, and we're again getting some store. And actually read stref does not change the store. So here I'm just going to use an as pattern, so because I want to return the store unchanged, but we're still needing access to the memory. So we're not needing access to the next. And what we're going to return is the current value of memory at position offset. That's our result of read stref. And as I said, the store itself is unchanged. So that's read stref. Then write stref is taking an stref and an int and an st unit.
Did you intentionally
write
write the prime?
stref. Yeah, I'll get there. I'm going
Okay.
to
All right.
like
Okay.
talk about the prime and the strictness in a moment.
Okay.
So
All right.
runST
Okay.
ref is going to take an offset and a new integer value. Let's call it I again. And again, we're going to get a store, and this time we're going to change the store again. So I'm going to pick up the memory and the next. And this time the result is trivial because the result is unit, right? And we're going to make a new store where we're updating the vector. So we can use this vector dash dash or slash slash operation, which takes a list of positions that we want to update. So we want to update the position offset, and we want to update it to the value I. And that is the new memory. And next is unchanged because we're not allocating a new variable.
Is the bracket too many there? Only one
Yes.
bracket before next. Yeah.
Yeah.
There you go.
Okay. And oh yeah, and then we actually want a strict version of writeST-ref, which basically ensures that we are writing values that are in weak at normal form. In this case, we can achieve that simply by making it strict or placing a bang on the integer argument. And and then modify ST-ref is actually not a primitive operation anymore.
So this now relies on the do on the monad
Yeah,
instance?
here we are for the first time using the do notation and therefore the monad instance, which does the obvious thing, chain the modifications on the store. So here we're taking the ref and we're taking the function. And what are we going to do? We are going to read the ST-ref and we're getting a value out. Ref. And then we're going to write the same ref with the value f. writeST-ref with the value prime. Yes. Okay, that is everything except for runST, right? So runST we also need, and runST we now hope to be able to implement simply as STA to A. Right, that's the point. And so we have such a make st function f here, which goes from store to a pair of A and store. So basically, we have to apply f to some initial store, and then we are not interested in the final store. The whole point is that in the end, we're taking the result. We're forgetting about the store. We never need it anymore. We can pretend it was never there. So we're going to simply take the first element of the pair. And the initial store is also easy because we can just use an empty vector and we can use 0 for first index. Okay. So now we've completely re-implemented our interface, and if we did things correctly, we should be able to copy in our classify function in exactly the same code as before, and we should be able to run the same example as before, and hopefully, sorry for jumping around in my editor a bit, we get the same result. So far so good, right? So
that's good.
For this particular use, everything is great. Okay. So now let's try to do something which is a bit evil. Okay. So I'm going to write an evil computation, and this is actually not a very difficult computation. We are going to write something which is of type stref. And how am I going to write something which is of type stref? Well, I'm going to use new stref and give it some value, let's say 17. And then I'm simply going to call runST on this. And that's fine, right? New stref gives me an st of stref, and runST takes any st computation and gives me what is returned by it. So now I have an stref.
It's type correct, so therefore it must be fine.
Yeah. Okay, so now I can use a function, let's call it eviler, because it is even more evil, right? And this one is defined as follows, right? We read from our evil stref, and we are writing to the evil stref the value x plus 1, and then we return x. Okay.
So
And
like x
now
plus plus, right, in C.
yeah, so it's basically just incrementing this variable by 1. And now I'm going to define test, which is of type int, because I have an stint computation, and that is simply runST of eviler. Okay, and that, I don't know, what should that be, right? I mean, if we try it out, what does it give us? It gives us an index out of bounds exception. And if you think about it, that is perfectly correct, because every time we're calling runST, we're allocating a new store, right? And so basically the lifetime of an stref, sort of the well-behaved lifetime, is intended to be only the scope of runST. But we are violating this implicit assumption by letting an stref escape from a runST computation, and then we're using it in a different runST computation.
Yeah,
and
the
that
wrong
is
store,
really,
basically, right?
that is really evil. What?
We're basically using a reference in the wrong store.
Yeah, so basically in a different store, right? And this is not exactly what happens with the built-in implementation of ST. We can still look at sort of the slight difference there, but it is conceptually very much the intuition behind it, right? So it's the runST that is selecting the context in which our computation is going to run. That computation, that runST is supposed to be in control of the local scope, and it's going to limit the local scope. And so runST decides how and where to run your computation. And this is kind of the motivation for this extra argument, because this extra S argument on ST represents something like the context in which the computation is supposed to be running. So if we now basically go back to the better type, right? So we give ST this extra argument, and then we basically give stref this extra argument as well. And then we are saying that if we allocate a new stref, then it is in the same context as the surrounding ST computation. So this is the same S as this S. And then we basically thread that through and go back to the original interface, except that we are still assuming that strefs are only of type integer. Right? Then at this point where we've done all this, we've really just threaded through an extra argument. There's still probably one more place where we need to do this. Right? So nothing changes. Everything is still as broken as it is. But we now have an opportunity to say what it means that an operation is sort of independent of its context, that it does not depend on anything that it shouldn't depend on. And that is exactly what we can express with this rank 2 type of runST, where if we say that this computation that we want to run should work in any context, and it is in fact runST that is picking the context, right? That is making the choice. And this is what I originally said, like a rank 2 polymorphic type is always flipping sort of the flexibility and obligations. The caller has now the obligation to provide a context-independent ST computation. And runST has the flexibility of choosing a suitable context. It's only surprising that we don't actually do it. It's all basically a phantom argument, a phantom type argument that we're never doing. But the net effect is that this A here cannot depend on S, right? The result type of the ST computation cannot depend on S, and that means that we cannot write a type correct computation such as evil anymore, where exactly that is happening, where we are having an stref which is tagged with the context of the surrounding computation, but it escapes from the computation that we are trying to run, right? And so you can see that the moment I added this rank 2 type, evil suddenly becomes type incorrect. And really evil is the root of all evil, right? I mean, it's not, eviler is not doing anything really bad. Like if we had something of this type in our scope, then everything that eviler is doing is fine. But this is already the problem, right? That we let an stref escape. And so this is basically showing the idea and the solution. And now I would like to go back in the final minutes to the original version and see that we can trigger problems there as well, only that they happen in slightly different ways. So let me go back to the original module. And let's try to basically create the same problem here as well, simply by giving runST a different type. I'm going to define unsafe runST, which has the type STSA to A, right? So I cannot get rid of this S argument because it's part of the built-in ST type, but I can get rid of the rank 2 polymorphic type. And how can I get rid of it? By using unsafe coerce. So how am I going to do it? I have this computation here, and I'm going to do runST, the original runST, and I'm going to use unsafe coerce on this original computation in order to pretend that it actually has the desired polymorphic type. And for that, I have to import unsafe coerce, right? This is only for the evil example in the end, right? Not for anything that we have been doing before. But now I can basically write evil in this setting as well, right? So I can do the same code that I wrote before, where I can, like using unsafe runST, I can let this stref escape, which I couldn't before, right? And so it's important that I'm using unsafe runST here. Again, if I would use runST here, this would be type incorrect. So unsafe runST, eviler as before. And now if I write test as before, which was supposed to be of type int, and test was supposed to be runST of eviler. And here I can actually use runST, right? I mean, it's really only this one place.
Like you said, the root of all evil is evil.
Yeah, so, and if I try to look at what test is, here I'm not getting an indexed out of bound, but I would argue that this is possibly even worse because I'm getting just the value 17, which is kind of fine because, well, so basically what the ST implementation on Haskell does, it allocates a global mutable reference, which actually does survive the runST call. And it is 17. And what eviler does is it reads its current value, which is 17. Then it writes it back to 18. And then it returns its value, which was 17. So we get this, right? And now if I write a function test2, which is also of type int, or it's not really a function, it's a value, and I give it exactly the same code, and I try to evaluate test2, then I'm getting 18, which of course is horrible, right?
This is awful, right?
Because now we have two integers which have the same definition and they yield different values. So we have basically found a way to re-implement some form of unsafe perform IO with all the negative connotations that has, right? So if you're using sort of like, if you would be using the unsafe form of runST, you would really do something very, very unsafe. And but the rank 2 polymorphic type of runST prevents this leaking of of references from their scope, because it allows runST to require that the computation we're passing it is context independent and is only using references that it defines itself. And that is a very nice way of ensuring this kind of safety. And similar tricks, I mean, that's also one of the reasons why I think this is a good topic for an episode. Similar tricks can be applied in other scenarios, right? So this is a common theme that you're trying to kind of define some sort of regional property of a computation where you want a certain aspect of it not to leak, and this technique of using a rank 2 type in order to prevent some aspects from leaking can be applied to other settings as well.
We have one final question, which I think actually would be useful to actually just to clarify. So they ask, how does A depend on S in the evil definition?
How
And that
does
is
A depend on S? I'm not exactly sure what the A is.
well, the A, that's the point, right? I think you're instantiating A to be stref s int, right? So if you look at what you're actually instantiating A to,
This A.
Yes, exactly.
The A and the runST, the
Yeah.
runST type. Yeah, okay. So
Right.
that is an interesting point. So if we just look at the new stref 17 computation, then this has the type sts stref s int, right? So it's an st computation which returns an stref s int. So the A value that we are instantiating either unsafe runST or trying to instantiate runST to is this stref s int, and this contains the S, right? So the instantiation, the desired instantiation of the A contains the S.
Yeah.
And if we have the normal type of like that we're using here for unsafe runST, then this is not a problem at all. We can choose whatever type we like, right? But in the quantified version that runST itself has, because the scope of S, because it's quantified, right, is only ranging over this expression, like the concrete value that we're using for S cannot escape. Like if A depends on S, then we would somehow have a quantified S that would escape its scope, right? And that is not allowed. So if we take runST here, that's why we get a slightly weird error message. Let's look at the error message also. I think it's a bit tricky to understand this error message. Right? I mean, but the point is it's about the scope of the quantified S being violated, right?
Maybe a way to understand this error message is that you said
Yeah.
it has type S, but GHG is verifying that it has some type S1 for some S1 that you know nothing about, right? And those two things cannot be the same.
Yeah. Or well, actually, I think it's the other way around. So basically, it's picking S1 for the one that we're using because that's, I think, the actual type, but it actually wants it to be of this sort of like universally quantified
right.
S, which is different. Yeah, but nevertheless, I mean that's the source of the type problem, but it's a desired type error, right? I mean it's one that we want to get.
One final question, which is a slightly higher level one. When would you use ST over state?
Yeah, I think this is an interesting question. I mean, so I think the benefit of ST is really in a situation where you want the in-place mutability, because I mean, state is simulated state, right? And it's perfectly fine for many purposes, like we did in our simulation setting. But then you can already see our simulated version of ST is not extremely efficient if you look at the because so vector indexing is fine, but but sort of like the in our case, the extension of the vector, the memory cells is problematic.
Well,
but
and the write
often
is
you have
problematic also, right? Because you're rewriting, you're copying the entire.
yeah, the update is problematic as well, right? I mean,
Yes.
so, but I mean, of course, this could be prevented by perhaps choosing a different data structure. But nevertheless, it shows that depending on your access patterns for your simulated state, you may really still not be quite as well off as you would be if you really knew that you have a memory location that you can destructively update. And ST is giving you that guarantee. And so in a situation where you want mutable state and you really want in-place mutability, ST is great. Another way to look at it is the other way around. Sometimes you start out with something which is an IO, and you're using IO refs because you're already an IO, but then you're noticing that you don't actually need anything else. That you never actually write to the disk, that you never actually do anything else, and then you can actually improve from IO to ST and actually use runST in order to turn it into a completely pure thing. That can also be a boon. Yeah.
There's actually one more question.
Yeah, sure.
Is S-can't escape its scope something that GHC just had to explicitly implement, and if they weren't careful, Haskell programmers could have let it escape? I mean, I can say yes.
Okay,
right?
so I mean,
this is the implementation of the type checker.
Yeah, I think, I mean, there's one point here which actually this question prompts me to, which I intended to say. So this, like, the idea of this is really, really old. So this goes back to a paper, as far as I know, to a paper, I think I have that here, called Lazy Functional State Threads by John Launchbury and Simon Peyton-Jones from 1994. It was published at PLDI 1994, and that is sort of in the early days of Haskell, in the phase between Haskell 1.0 and Haskell 98. And I think this was one of the first uses of rank 2 polymorphism at all. I mean, perhaps, I don't know the exact history there. Perhaps GHC had it. Perhaps GHC even implemented it as some sort of special case for runST. I don't completely know, I must admit. It's like three years before I first used Haskell, so I don't quite remember the history there anymore. But I can imagine that this was part of the motivation of getting the sort of rank N or rank 2 or rank N polymorphism story in the type checker really right. But the great thing in a way is it's not a special case scenario. So even though, yeah, sure, in a way, the type checker implementers have to do their job well in order to actually make this work correctly and prevent the wrong properties from occurring and like make everything work fine, it is actually a general purpose concept which can be applied to this sort of problem, but rank 2 or rank N types have many other uses and practice as well, and so you have to get the type checker correct once, and then the rest just falls out of that general principle.
Okay.
Cool. Then I guess we are going to.
Thanks everyone for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe. We'll actually keep the chat open for a few more minutes, so if you wanted to ask some questions, put them in the comments or in the chat box, and we try to answer them. And if not, feel free to put messages on the comments below the video, and we always try to address as much of those as we can. So, hopefully see you again soon. We're not actually sure yet exactly when, but probably like a week or two.
A couple of weeks,
a couple of weeks
usual.
Yeah.
Okay.